Okay, so let's wrap it up. So first, we had a look at a bit of graphics, a bit of history, a bit of principles of how to model graphics, right? So especially in a 3D sense, 2D is relatively straightforward. But let's bring it back to mobile development. You know, what has happened, what can we do, and you know, what are the directions in which graphics on mobile is gonna move, right? That's one of the things. One of the probably more popular examples that you guys still recall, hopefully, Snake. How many of you actually played Snake? Okay. How many of you only developed Snake? Because that's usually a good entry level exercise, programming exercise, right? Well known. So yeah. So you know, very popular game. You remember that in the 90s, end 90s, 97. And I think it's still supported in a way. And you know, the various versions coming out with, I think, even 3D variants and so on. Could make an interesting exercise having a 3D version of Snake actually on. A bit creepy, I guess. Anyway, so a very popular game at that time, right? So Nokia phones particular, and at this time, apart from having the native development environment that was particular to specifically Nokia phones or the built-in games, Java was of course very popular at that time, being a child of the 90s in a way. And there were various editions, including Java, the main edition the standard edition that you guys are acquainted with, I assume, but also the mobile edition actually. So at that time, before Android, before iOS, most smartphones had so-called Java ME support, and that basically was a subset of the actual Java functionality for mobile phones. Yeah. So if you're comfortable with Java now, you kind of would have been comfortable with Java on mobile phones. You would have far less capabilities because simply many of the concepts were too heavyweight. You wouldn't have things like an observer pattern built into a language. I think no reflection, and it's a lot of cuts here and there. But fundamentally, you have a Java version you can develop against, and this is basically a basis for the contribution of third-party games, right? Oftentimes quite questionable ones with interesting marketing schemes. You guys may recall Jamba. That's one of the subscription schemes that you could have had at that time. It's pretty much equivalent to an app store in a wider sense, but you basically just, you know, I think you did SMS based and you basically download the corresponding game or ringtone and so on, right? So relatively simplistic, but that was quite hot at that time. So it was, if you did mobile development at that time, it would have been something you would have come across. So until, I think, well into mid-2000s, in fact. So then the first actual phone that had, or actual operating system rather, that had decent 3D support for actually doing something in the third dimension on a mobile device, and had also smartphone capabilities, was basically supported by Windows actually, right? So they were, we always get the impression that iOS was basically defining the market, which it ultimately did, but the first innovation actually came from the Microsoft side. Never really became mainstream and had OpenGL ES 1.1 support. We get into that in a second, what that means. But you could fundamentally do similar to the cut-down version of Java for mobile devices. OpenGL ES embedded systems is basically a reduced version or a cut-down variant of the fully fledged OpenGL that you get, you know, with your modern operating system / graphics driver on your laptop or desktop machine nowadays. So the idea was there, okay, can we unify the development environment both for mobiles and for desktops already, right? So of course the capabilities were somewhat limited, both in terms of representation, even the pictures look good, and of course also the impact it had on runtime of mobile devices, right? So because the load of 3D was challenging for desktops at that time, let alone for mobile devices. Then we got the good old iPhone finally, right? So suddenly there, you know, was much more performance available suddenly, right? So and also flexibility available, and a range of frameworks came out that actually supported the development of 3D games in particular on smartphones, because smartphones were basically enriched by having all this rich sensor set by allowing you to basically use the phone orientation as input device, for example, for racing games, which made it much more attractive than trying to deal with those limited abilities that earlier smartphones actually had available. And along with this was basically the development of OpenGL, the extended development of OpenGL over time. We talk about OpenGL again. I mean, just reference it here already because it's quite relatively way off. But nowadays, of course, Apple has turned away from OpenGL, so they have their own, or they're putting their eggs into one basket. In this case, mostly Vulkan, which we briefly chat about as well in a second. But fundamentally, the idea is there's a rapid progression of frameworks that you can use with this. For 3D game development in particular. So the iPhone was of course also the first phone that had actually decent GPUs. I mean, like graphic acceleration on board, allowed good integration, and also of course with all those frameworks they came at a price. You basically have massive lock-in, right? So you can only use those frameworks on top of OpenGL with the device itself. So which kind of make it challenging actually to have games that would be cross-platform, meaning also run on mobile, on Android devices, unless you of course invest significant into cross-compilation efforts or the like. Nowadays it's even harder because they officially don't support OpenGL anymore. So yeah, again, the standard approach of course is to basically think about how to or monetize the net. On Apple's part, it was basically via the App Store. If you log in the gamers with respect to the supported environment, then of course you bind them or tie them specifically to the Apple App Store as well. And then if you take 15% for subscription and 30% for any sold app, that's a good payoff. So there's kind of some incentive of providing this facility for mobile devices. Yeah, so just some intuition as to how mobile apps actually have are positioned roughly right now. We're sitting. This is 2017, admittedly, but the data is kind of really highly variable in terms of the accurate information. In fact, I think the number of apps are currently going down quite a bit because there's more rigid monitoring has been introduced on Google's side as well as Apple's side, but specifically Google's side. So actually, the number has gone down. But just to get a feel how the rough distribution is. And then you see actually how they earn money. Well, not with games, but actually by providing relevant and up-to-date platforms on their respective for their respective operating systems, right? So, okay. So, but looking at the progression, it's quite phenomenal compared to desktop devices. How far we've come, right? From 1997 to 2018, seeing here as games that you can play on mobile devices. Right side high performance GPU-centered games. So that's quite a progression that has been made, much more relative to the PC side, where it's, I think, since at least the 2010s, reasonably stagnant in terms of performance increments compared to mobile. Okay, so I talk about frameworks a lot and the login, or a bit and about the login that's associated with this, but it's important to know actually what are we talking about. So there are two major frameworks that were historically particularly important. One of them OpenGL ES, embedded systems in various versions. And the thing about OpenGL is that it's fundamentally platform independent. So it has been built in a way that it actually runs on any sort of platform, including desktop and mobile device. Again, iOS abandoned it for various reasons, but it was widely spread, meaning if you develop your application against OpenGL, chances that it runs on a wide range of platforms with minor modifications, but modifications is quite sensible. The thing is that OpenGL basically specified a set of functionality that your GPU needs to provide. It's kind of an independently specified API by the so-called Kronos group, and that is basically somewhat industry-sponsored, but not necessarily tied to one particular vendor. Therefore, kind of independent, and it's openly licensed. And vendors can then implement functionality, meaning if there's a function call to, for example, rendering the vertices or those different geometric primitives that you can render for given vertices that you are given, the API is standardized by Kronos Group, but the implementation is then on the vendor side. How it's done on a graphics card is up to the individual vendor. And that's where the performance comes in and the proprietary nature. We don't know how it's implemented, but what we do know is the rough functionality that is supposed to be provided, right? So OpenGL is an API. It's not an implementation per se, right? The implementation is manufacturer side problem. That would in our case be AMD or NVIDIA with their respective drivers that consume the OpenGL commands and basically ensure corresponding representation in 3D. So, and similar for Android and of course iOS. And we'll see in a bit how that works. The corresponding counterpart for Microsoft, because it needed to be different, was basically DirectX, right? So it's also built on similar principles as OpenGL, but it kind of died with Windows Phone, so it doesn't really play a role anymore in the mobile arena. Of course, in desktop it still does, for modern games anyway, especially with Xbox. Gaming consoles still drive it, but from a mobile perspective, it's not really something to look at. What's more important, however, is to understand how this OpenGL exercise works, right? Because talked about it a lot, but told you relatively little. Well, the idea is basically to automate the rendering process as much as possible. So you, as a developer, you think about having models of your scene, if you wide a sense, based on vertices, right? The individual three-dimensional points, if you like, vertices that you are feeding into the pipeline, right? So think about it like a state machine. So you feed something in, and you press a button and say, process, and then magic happens and hopefully comes out on the other side, right? So it's considered a state machine. The approach is somewhat conceptually single-threaded, right? So it takes one step at a time. Inject all the vertices, combine the vertices, generate meaningful shapes out of this one, perform some rasterization, we'll get to that, and basically then augment it with color and bring it down to a screen-size representation. So what's actually happening? Well, the earlier version of OpenGL basically allowed you to provide very primitive parameterization of the pipelines. You would say, okay, here are the vertices. I'll tell you how to combine them into faces, right? We saw the primitives before. So you could say, for example, combine all of them as triangles. So you have a set of triangles, or draw lines and so on. All the primitives that you saw before. So that's something you can actually provide as information. And then the idea was that you provide lighting. So not only do you have a scene, but you also have a certain camera position. I think they had fixed support for up to 6 or 8 cameras. I forgot it right now. That could be at a given position. You have these objects, the vertices, that of course at a given position, because you provide the position information implicitly with the vertices, and you had light. So somewhere in the scene there was, you could position lights, and that would basically shine on the object. Because if you have a scene without light in OpenGL, good luck, everything is black. That's not really helping you, of course. So you need to have those components. But in the original OpenGL, without the programmability, it was basically straightforward that you just provide those parameters, and then you just say, GL draw, basically draw this entire thing, and it would come out the way you would expect it, right? But you have very limited opportunity to intercept or to vary the work with the pipeline itself, rather than just putting stuff in and expecting the same to come out, or the rendered version to come out. So in OpenGL onwards, 2 onwards, there was suddenly the idea of, okay, let's make the pipeline more programmable. We keep the same concept, but instead of just allowing this very simple primitive combination that we're doing, can we actually provide the developer with richer capabilities? So, and the idea is here that we then could program the vertex shader and the pixel shader. Well, or it was later called rather fragment shader, as we'll see in a second. So the idea is here that once you inject the vertices into the 3D world, in the vertex shader you can still, the concept of shaders is basically, or in the previous non-programmable version, the fixed pipeline OpenGL version, you'd basically inject the vertices, everything would run through and come out on the screen and so on. But fundamentally, you would do the programming on the CPU in C++, for example, and provide this information, upload the information, and then execute it. Shaders were programs, or are programs, that you can upload to the GPU itself. So suddenly you can modify things on the GPU itself and provide more complex activities. So every time you read shader, it basically means program on the GPU. So, and the vertex shader precisely allowed this. So you suddenly were not only, of course, allowed to inject the vertices, but you can modify them on the GPU. You can change the positioning, for example, or you can remove some vertices, or add additional vertices, or do some manipulation in the GPU itself. And the great benefit was that it's way faster. So you could have a base model, and you can modify and manipulate it later on. So it's one of the key things. So then after that, the original idea of actually combining those individual vertices into primitives is applied. That's automated still, right? So you basically just tell the system, or in the OpenGL 2 version, basically tell the system make triangles of all the points you got right now, right? So, or just lines for example, right? Then rasterization. Rasterization deals with the fact, here we are dealing in a 3D representation that is purely geometric. We're only thinking in terms of geometric shapes, triangles, quads, and all that kind of stuff. Here, rasterization is about, okay, this is more related to the display device, right? So now we need to break it down into a pixel representation, right? Because in 3D, we don't think in pixels, right? Pixel was a 2D representation problem. It's basically links to the resolution of your monitor. Okay, how do we represent this on a 2D sphere, right? And it also boils down, for example, to deciding, okay, if you have a 3D model, right? And for example, we're turning this 3D model, right? Which faces do we actually need to represent, assuming that your display or your viewport is basically here? Well, everything that's on the back doesn't need to be rendered in the first place, right? It's also about removing, avoiding the processing of unnecessary vertices in the first place. So that's the idea of breaking it down. So rasterization was basically the initial stage of actually identifying, okay, what's actually relevant. The pixel shaders then, which you can program as well, now called fragment shader, as I mentioned, allows you to manipulate the color of the individual pixels, right? So once you have the geometric shape, once you modify the shape for representation on a 2D screen, then you can modify color information in the OpenGL pipeline itself for all the pixels that are eventually drawn anyway. Yeah? So here, no longer geometric shapes, not that stuff anymore. Here we are like, you remember the deer picture, you only work on pixel levels basically, right? So that's usually where color is added. Well, and then you can apply some additional effects, such as, how do you say it? Depth effects, for example. We know that object at distance are not only smaller, but they can be plotted with or rendered with a smaller resolution because we don't see the details anymore. You can introduce aspects such as fuzziness, anti-aliasing. What's anti-aliasing? Correct, right? So if we have the nice geometric shapes here, well, if you zoom in far enough, it actually looks, really, really cluttered, right? Because you suddenly see, oh damn, based on the rasterization, I actually reintroduce artifacts because I need to represent a diagonal line in, a quadratic pixel form and so on. So this is where then all those automatic operations can come into play. This is just a matter of parameterization, so there's no programming involved. That's really done for you. That's the neat part about it. A lot of stuff is just using built-in algorithms to do that for you. So that's the really quite neat part. You only technically need to deal with your 3D model, and if you want, with some color modification. So once that is done, it's spit out onto your screen. Right? So then OpenGL handler gives us back to a so-called window handler, which is not part of OpenGL. It's usually specific to the target operating system, what you use to display it back on the screen, basically. That's the whole process of how it works. Does it make somewhat sense intuitively? It's not really in depth here right now, but can you follow the idea? It links back to the original problem that we need to represent 3D and 2D effectively, right? Take 3D in, do something automatically, for example, generating those shapes. Those shapes, right? So spit in, okay, please make a triangle strip and so on, and then populate things with color, and then spit it out basically on the other side, right? So that's the rough idea. So over time, so that what I showed you before was OpenGL 2. Now this we're looking at OpenGL 4 because the time moves on. So what did they actually add to it? Fundamentally, it's the same principle. It's always about addition, right? So in addition to the vertex shader that allowed it to modify individual elements, we have a tessellation shader, what it's called. This is, for example, dealing with challenges such as detail. Remember the image, the contour I showed you, which was rather coarse-grained, and I asked how we can refine the quality of it? Well, you can refine it by having smaller triangles, effectively, right? So, and here, this tessellation shader, for example, is really good at this because it allows you the automated subdivision of shapes into smaller shapes. So you can basically automate this generation of additional vertices on the fly using that shader. We basically take a triangle and subdivide it into smaller triangles for you, right? So the input would still be the vertices, the original vertices, but in the GPU it would actually introduce new vertices, for example. Right? There's a geometry shader that you can program. For example, if you're not happy with those few geometric primitives, such as GL strip, GL line, GL triangle, GL quad, you can develop your own ones, upload them as well, so you can have more advanced primitives as well. So that's what's part of the geometry shader, what it can do and so on. So basically, it's basically just extending the pipeline, but fundamentally, the principles are always the same, right? You have 2 points of modification. One of them is, what can I do with the vertices, right? The individual points making up the 3D models. What can I do prior to output, right? So how can I modify the final output? So that's fundamentally the idea. But the principle remains absolutely the same, that you basically have a state machine with some input on top and then some output at the bottom plus parameterization. Any questions regarding this? It's very brief, I admit that. I don't think we asked nasty questions about the exam. I just want to give you an intuition as to what the graphics, how the graphics thing works every time we talk about OpenGL, what it actually entails, and what is automated and what is not automated. So just now with this spec drop, perhaps it's easier to appreciate some of the introduced features, right? So we talk about it. So the first of all, OpenGL ES embedded system, we got that bit. The OpenGL ES11 was basically the fixed function pipeline, right? So I mentioned before, fixed function basically means that lighting, texturing, the vertex transformations, and all that kind of stuff is built in. You have only, well, it's good and bad at the same time. Good because you have, it's a lot easier to program because you need to write these GPU programs, the shaders. You just parameterize the pipeline and say, take my vertices and print them, right? Get it done, get it over with. But you're limited, right? So you have certain camera positions, lighting, only a few number of lights and so on. So it makes it slightly less flexible. And here OpenGL ES2, that's kind of the minimum baseline, I guess, nowadays, is that you have this programmability of the 2 shaders, right? The vertex and fragment shaders, and so on. So from a graphics point of view, OpenGL 2, you're kind of in a kind of reasonably safe space. In an OpenGL 3, you probably know about GPU processing and so on, right? So the whole discussion about cryptocurrency mining and so on, where you actually use GPUs for computing, hashes, for example, as opposed to using it for graphical output. So basically compute shaders, uploadable programs that only do operate on graphics memory, but actually don't produce visual output. Right, so you use them for computing. Were introduced in OpenGL ES3 onwards in particular, right? So you can actually do GPU processing on your mobile phone as well. So that's the fundamental idea. And of course, then there are higher versions that introduce additional features, such as this sessionation, I talked about it. There's also specific Android extensions in terms of the API. So there's certain functionality that's only available on Android, but allows for richer visual output, for example. And then OpenGL ES 3.2 roughly corresponds to OpenGL 4. That was the pipeline you just saw with geometry shader, tessellation shader, fragment shader, and so on. So there's a bit of an offset in terms of the version numbers, but fundamentally that's the idea. Those are always cut down versions of the fully fledged variants, of course, right? So you can't just say, oh, cool, I have a game, OpenGL version 4, I run this in OpenGL ES 3.2, good luck. That's not going to happen, but you can roughly assume an equivalent feature set. There, that's the idea. So, and if you're wondering which version supports which, as of Android 6, you would have OpenGL ES 3.2, right? So if you're running this or later, so Marshmallow or later, you'll be fine. You basically can do all that already on your phone as well. And Android 7 onwards also has Vulkan as another API. I'll allude to very briefly later, which is kind of up and coming in a way. Does anyone have? Did anyone hear about Vulkan in any specific context as a graphics programming API? No? The gamers amongst you? Excitement? No? Okay, I sense that. Anyway, so yeah, that's a rough idea, right? So cool. I talked about this briefly. Yeah, basically that's roughly of how the first version was work. You would set some sort of textures. You said, okay, how you what operations are you doing on the final output? Depth test state basically figures out, okay, you have this tiger here, right? Figure out which vertices are actually not visible and discard them from further processing. So we don't process stuff we don't see in the first place. Then you switch on off some functions. Environmental mapping, for example, is for reflection. So if you, for example, want to have a reflective effect on the environment, assume you have a teacup or something, or want to emulate a mirror behavior, right? You would just switch on and say, well, this object actually has environmental mapping of reflected, and it would basically just project a view in the opposite direction onto the object, right? So it's a very cheap way of having mirroring that basically emulates how this environment would look like and just plot it on the object. So you can switch that on and off as well. Then you have lighting. Lighting can be positions, brightness, orientation, positioning. Camera, same. And then basically you can say what transformations to apply. Transformations refer to the positioning of the object. So the object is uploaded into the pipeline, and you can say, okay, I want to turn it to the right a bit, right? Or I want to translate it, move it up to the top right, right? Or you have rotation, you have translation, which is moving, and you have scaling, right? All the kind of stuff we talked about briefly in animations as well, roughly the same, right? So fundamental transformations, so rotation, scaling, and translation. So you can do the same here, of course, as well. And once you're done with this, you just say, okay, draw this whole thing, right? So that was the intuition there. Quite straightforward. Yeah. So in OpenGL ES 2, you need to do more, right? The transformations is something on you. The lighting is also on you as well as the cameras. So in OpenGL ES 2, so in the advanced version in practice, it would mean basically you set the baseline parameters again, similar to the first version, but now you upload the shader program, you link the shader program variables to your C++ code, basically say, okay, this is basically the input variable for the shader program. You kind of need to link your actual game, if you like, with the graphical output to some extent. Basically then you upload the model data, meaning the vertices, and then just say basically draw it. You need to do everything yourself. Anyway, there are helper libraries for that purpose, but fundamentally it's much more up on you to do transformations, so turn the object in 3D virtual space, position the lighting and positioning of the camera, right? So it's kind of the things. Yeah, so it was basically, so just to get an idea about OpenGL ES 3, what can you do with compute shaders? Well, you can do quite a bit. Of course, here's examples of visual output. Surprise, surprise. Otherwise, it's a bit boring. But fundamentally, you don't require visual output. But the idea is here. Let's use the graphic. Or what makes graphics cards or GPUs so specific compared to, what makes GPUs different from CPUs actually? Why is everyone so hard in using GPUs for pretty much everything as soon as they can? I would just beef up CPUs even more and screw the graphics up. Please.
I suppose because GPUs are specialized for graphics processing, whilst the CPU is more like it does all logic the computer might need.
Yes, that's part number one. So the CPU is kind of a system processor, right? So it facilitates all kind of interaction in the system. It needs to deal with I/O. It needs to deal with processing of application state, logic, and it needs to be kind of general purpose as well in a wider sense, right? So a wide array of operating system, programming languages, and so on. A lot of compromises, and of course we also have a bit of legacy problems there because it fundamentally needs to be compatible to the x86 instruction set, meaning every time you need to support legacy architectures, you usually sacrifice performance to some extent. So there's something there as well. Is that the only thing? What else? Architecturally, how are they different? CPUs and GPUs. Well, the fundamental difference is that in GPUs they are more specialized and they have different means of dynamic organization. So you have the GPU facilities with a lot of individual cores that can be reorganized and combined into so-called working groups, right? That can work on related issues together. So it makes it more flexible in the application, but more importantly, they are much tighter linked to the memory, much closer, because the graphics card comes with its own dedicated memory. And the memory that's available on the graphics card is linked at a very high, has a very tight link to the actual GPU, the progressive processing units. And we're talking about bandwidths of hundreds of gigabytes per second, whereas CPUs, we're talking about tens of gigabytes per second. It's fast, but not as fast as it is for GPUs, basically, because they're so there's the proximity aspect that they're co-located, but also that they are so specialized, you mentioned that before, that the memory is really highly optimized for the use by graphic processors, whereas in a CPU we have much more general purpose components. I mean, you can dynamically plug in and out different memory and different memory types into your system, and it's always mediated via the system bus, right? So it's not immediately attached to the CPU, but actually to the chipset, and that usually sacrifices performance considerably. Let alone the organization of the CPU, which is usually organized in few cores that are need to be kind of dynamically grouped by the operating system, but can't be systematically grouped as it's done for GPUs. So architecturally, there are two advantages. One of them is that mostly GPUs are really dedicated only to be workhorses. They don't need to do elementary system functions. They don't need to bother with that stuff. And simply that they're tightly bundled to their to memory, which makes them significantly faster. So, so how does it fundamentally work? Well, fundamentally the idea is basically they work on the same kind of concepts that we use for graphics programming in the widest sense. So we have some sort of shader information. They have some link information from the invoking CPU code, basically, you know, to parameterize the input. So it's kind of a buffer memory that this is GPU, this is kind of the intermediary memory. This can be written to from the CPU. This will then be read to from the GPU. So basically that's the interaction means. So we have the programs, we have the parameter values for initializing the shaders programs. We have the texture information. And that's basically a buffer you can populate with you know, texture information that is like images overlaid over given objects. We didn't really talk about this part, sorry about this. So if you have your geometric shapes, you're generally overlaying them with a picture. Think sprite again, right? So the sprite is kind of put on that tiger in order to, for example, model the fur patterns or something like this, right? But it fundamentally is just aligned and adjusted to the shape that is provided by the 3D model itself. So anyway, so that's the kind of stuff that's stored here. That's the then we have the actual image buffer that we can use to provide the input vertices, but also the output. The results are also stored there and can then be consumed by the CPU again. Right? So that's how the interaction basically works. Always mediated by a high performance memory, but the GPU itself works basically well with highly parallelized data, because the individual cores work individually. If you have tasks that are totally independent of each other, right? So for example, cryptocurrency calculating hashes, right? The calculation of one hash is independent of calculating another hash, right? If you try to kind of do some brute force activities, or, you know, again, cryptocurrency mining, it's perfectly aligned with the idea because you can parallelize the work easily, right? You don't have any need of dealing with concurrency, meaning you don't need to integrate results in any way afterwards. So meaning one execution doesn't need to wait